So welcome to the last session for today, where we have two presentations, starting with the first presentation from the Trinity College in Dublin, and Anil Kokaram will give the presentation about demystifying the use of compression in virtual production. Anil graduated in Cambridge with a PhD in 1993, and further got also an Amherst Science and Engineering Academy Award in 2007. He's now the chair and professor of the electronics at the Trinity College in Dublin. So welcome to the stage, Anil, and enjoy your presentation.
Okay, thanks very much, Dagmar. What did I do?
Bro, something's fucking
somewhere
wrong. Something is wrong.
Clicker. I have it. Just gotta find where it is. Any minute now. I got it there. Yeah. Thanks a lot. Okay, so thanks a lot for that introduction. This talk is really about picture quality and the impact of compression on picture quality in virtual production. So I guess after all the talks this morning, you already appreciate that virtual production really is an amorphous term for a grab bag of technologies that streamline visual production. The workflows and technologies are sufficiently complex that SMPTE has started the Onset Virtual Production Initiative, which tries to standardize or define best practice and help to accelerate interoperability between these technologies. Now, the particular technology that we're talking about in this talk is sort of illustrated here. So you could see the LED wall in the background, which is displaying some background plate. And then both foreground and background elements are being captured in the camera and visualized on set and eventually passed on to post. Now, the accepted wisdom is that if you're driving a screen in a virtual production environment, then you need near lossless compression for those pictures. And the rationale is quite strong. So first of all, virtual production does require real-time, low-latency video playback. And then because you expect losses in the system, it makes sense to drive that wall with very high-quality source footage. You put those two things together and you're inevitably led to looking at a series of proprietary near-lossless codecs for compression, like these three here, Notch LC, HAP, and Daniel 2, and we'll be looking at that during the talk. But what if the loss in the video wall is actually more than the loss caused by compression? In that case, in fact, there are a lot of other codecs you could be using which use multi-frame compression to reduce bitrate to a very great extent compared to these proprietary lossless ones. And GPU hardware already provides these things at high speed and easy to access. So why not investigate these things as competing standards? So in this talk, what we're going to be talking about, first of all, is presenting a methodology for measuring picture reproduction in VP setups. We'll evaluate a bunch of compression options, about 6 of them, talk about perceptual metrics, and then I'll look at bitrate quality trade-off, and then make some cautious recommendations. Now, this work is the result of a collaboration between ourselves in Trinity and Disguise, and we're part of the EU project Emerald, sponsored by the European Union Horizon Fund, and the underlying subtext here is sustainability and AI in production. So we're trying to reduce the resources that you need, in this case, for a virtual production scenario. So I'm going to be talking a lot about video compression, just to demystify some of those terms. all codecs today are hybrid codecs. You have these keyframes which are intra-coded like JPEG, distributed throughout the video sequence, and then a bunch of intermediate frames which are predicted based on those keyframes, and they're called P-frames, and you need to use motion compensation for that. The other reason why more recent codecs like HEVC and AV1 perform better than previous codecs is because they use block sizes which are correlated to picture content. So high texture means small blocks and low texture means big blocks. So there are three issues of concern for any technology in virtual production: speed, latency, and picture quality. Okay, I'll try and shout. So speed, as far as speed is concerned, we measured the encoding speed using these 6 codecs across our data set, and we found that all of them perform quite well, of course. It's all right. I'm used to this from school. Okay, so we're comparing 6 codecs. They all perform very well as far as encoding is concerned. In fact, off of the GPU, 3 of those codecs, AV1, H.264, and HEVC, all encode faster than about 50 FPS. So speed is not an issue. Latency is not an issue because I'm going to be using intra-coded or prediction-only formats for the 3 modern codecs that we look at here, AV1, H.265, and H.264. And then we're going to look at 3 other lossless, near lossless proprietary codecs, NotchLC, HAP, Daniel 2. So latency is not an issue in this comparison. So let's talk now about picture quality. And our environment configuration looks like this. We have a red camera recording an LED wall, which is it's about 5 meters across and about 3 meters high, not quite a big wall, a development stage in London. We're capturing at UHD1. Everything's gen-locked at 30 FPS. We're going to use this zoomed-in configuration, so the camera zooms into the visible part of the LED wall, and the entire field of view of the camera is occupied by that display. These are the 4 pictures in our data set. So they vary in bit depth between 10 and 8 bits, resolutions from 1080p up to 4K and DCI 4K, and different complexities and so on. They're short clips, just 7 or 5 seconds long. And notice the QR codes in the corners of each frame. You need that to be double sure of your gen lock to make sure you compare like with like when we do the comparison. As far as video quality metrics are concerned, we're going to be using PSNR, but we're also going to be using 2 perceptual metrics, VMAF, which is a well-known metric from Netflix, and color CVVDP, which is a metric coming out of Cambridge University that also measures color and perceptual color artifacts as well. And those 2 metrics give us the perceptual flavor of this study. Now, before we even get to the screen, we could look at classical compression performance of these different codecs. There's a lot of information in here, so we're going to go through this a bit slowly, right? So the x-axis in all of these graphs is bit rate in a log scale. Otherwise, the comparisons would look, really, really too much to believe. So log scale bitrate on the x-axis. On the y-axis, on the left-hand side is VMAF. On the right-hand side is PSNR. So you want to have operating points to the far left and high up on these plots. So if I look at the red line, for instance, that represents the performance of HEVC on the left-hand side. You see you have, 5 operating points there, and we just connect them with a straight line. Each one of those points we discover by changing the Q parameter in the codec, and it lets us map out that curve. And that performance is way better than the brown line towards the right, which is Notch LC. So Notch LC gives you 100 VMAF at 2 gigabits per second, but HEVC and even AV1, which is the green line, gives you 100 VMAF, which is the best performance at way better, about 100 megabits per second. So if I draw a straight line between those 2 points, you could see that even before you hit the screen, you could save 20 times in bit rate just by using these performance characteristics. And you could do the same thing for H.264 and Daniel 2 and so on. Those are all the different codecs there. If I change my y-axis to PSNR, you see I get the same performance, right? I could do the same thing using Notch LC as a reference, which is accepted in the as a standard to drive virtual production walls. You could see here that you could still save a factor of 20 in bit rate going from that Notch LC across the AV1 or even HEVC. Now that was using intra-only frames, so every frame independently encoded. What I could do instead is to use only one keyframe and predict all the other frames of my sequence from that first frame, and then you get even more separation. So now I could save a factor of 100 in bit rate driving that screen, and I don't lose any quality. Now, this is before we get to the screen and before we visualize those pictures, right? Oh yeah, and by the way, this just shows you that that savings is content dependent. So for waves, we only get 2 times, and for TIFF, it's about 8 times. So let's think about the screen now, right? I'm going to take up a sequence, then I'm going to encode and decode it at some bit rate, and then I'm going to drive the LED wall. We're going to capture that in the camera, and then record the reference pictures, raw pictures driving the screen, followed by some sort of encoded, compressed picture decoded to the screen, and compare those 2 signals and see how close they are. So in the setup here, some details important, like we're going to add QR codes at the start, and those 2 yellow circles, all I'm trying to show there is that we're going to normalize all our captured pictures to 444 and UHD1 at 30 FPS before doing our analysis metrics. So that might seem sort of involved, but at the end of the day, this is what we end up with. So the top there shows you the film strip that we end up with. On the far right is our reference playback, and I show 2 different versions of that reference playback. So the reference playback is the raw data driving the screen captured in the camera, and the middle playback is some compressed version, maybe AV1 at QP40 driving the screen captured in the camera. And then way on the left might be H.264, for instance, right? And we want to find out how close is the quality of those representations compared with that reference sequence on the right. So let's look at some pictures now. Here is that TIFF text sequence, which contains text and some graphics and so on. This is the source video on the disk before we play back and capture. And you can see the QR codes going there. Now let's look at that green crop, right? So on the left here is the reference material played on the screen, recorded through the camera. And on the right is Notch LC. So you take the Notch LC stuff, play it on the screen, capture it in the camera. And you're not going to see any difference between these 2 signals, right? Notch LC is at 400 megabits per second, is more or less lossless anyway. So let's push this a little bit further, right? So on the left here is Notch LC, the same thing that was on the right before. And then on the right is AV1 intra-coded. So we have 4 times less bit rate on the right compared to the left, but you're not going to see any difference. And we could push this further, right? I could change the right-hand side to have 1 keyframe. So now I have 6, so the file on the right is 6 times smaller than the thing on the left. And you're not going to see any difference either. Okay, so let's think about some numbers here. Let's try and measure these savings. We're going to use Notch LC as a reference quality because that's what most people are happy with driving their virtual production display. We're going to ignore everything which doesn't give us VMAF of at least 90, because over 90 is more or less perceptually lossless. And we're going to say, right, let's look at the lowest bit rate of Notch LC, which is bigger than 90. Use that as our reference and go horizontally across and see how low we could go with AV1 and H.264 and so on, and hit the same quality level. So we're back to those complicated diagrams. Again, in both cases, x-axis is log scale bit rate. Y-axis in both cases is VMAF. Left-hand side is intra-coded frames, independently encoded frames. Right-hand side is only one frame, key frame, and the rest predicted. And you could see here, first of all, everything below 90 we ignore, so Daniel 2 doesn't make it for this particular sequence. And if I do this trick of selecting the lowest bit rate that is over than 90 as Notch LC as my reference and go right across, you could see I could save 11 times bit rate with AV1, a little bit more with HEVC, with intra-coded on the left. And if I have one keyframe on the right, I could save 20 times in bit rate. If I do the same thing with the color metric, I'm going to get almost identical pictures. So this summarizes the performance across the 4 clips that we have. So the point here is that, the savings are multiples of higher than 20% anyway. If one thing to notice here, we don't have H.264 for 2 of the sequences, and the reason why is because you don't have a 10-bit invocation of H.264 on the NVIDIA chipset, right? So we just don't have it there. Now, this is for intra-coded, and you can see I have huge savings for some signals and not so much for others. If I go to one keyframe, the only takeaway here is that the shaded bars are bigger than the solid bar, right? So if I use one keyframe, I could save even more bitrate. The one standout is waves, and waves is a difficult sequence to compress. So you only get about 70% improvement in bitrate. So this is the wave sequence. And you can see there's a lot of interesting textures, overlapping areas, transparencies, and so on. And here on the left is the Notch LC rendition, and on the right is AV1, keyframes only, 70% decrease in bitrate. And okay, you can see noise from the camera recording, but that's sort of variation in light caused by water moving over the reef and so on. That's special stuff for these guys and pretty challenging. You could also see a moire pattern in the LED display here. So, to wrap up then, first of all, what I've done here is to compare picture quality where it matters, which is in camera and not on the disk and not in the screen. And the way we set this up, we have a reference picture played through the camera, and we could compare with renditions played through the camera or rendered through the wall through the camera. Genlock is a huge issue. I didn't talk about it a lot, but I noticed a lot of speakers also mention how important Genlock is. And we use QR codes to double check our Genlock all the time. If you look at the table on the right, what we've done is taken an average over the measurements that we can make from these 4 sequences. And you can see the modern codecs, HEVC and AV1, could give major reductions in bitrate compared to the proprietary codecs. So modern compression could have a positive impact on file size, and AV1 and HEVC definitely competitive because of the speed and low latency implementations available on the NVIDIA chipset. So a couple of final comments then. First of all, subjective assessment. We're looking at that right now. We have 2 opportunities for subjective assessment. One is, put some people in front of the screen and rank them on a Likert scale, or rank the pictures on a Likert scale and so on. The other one is to look at the pictures rendered in camera and perform the same experiments. So final takeaway then is that we would recommend looking at AV1 and HEVC as viable alternatives to driving LED panels. And using intra-only modes for these codecs is quite safe, latency safe certainly, but you could push to about 5-second GOPS and double your gains. And I would actually recommend that option. Okay then. Thanks very much for your attention.
Yeah. Any questions in the audience? Now it's working.
Thanks for that presentation. I was just wondering if you had any view of what the quality of your pictures were like in terms of the metric results you were getting back. So I know we were getting a lot of averaged picture quality scores back, and maybe it was across the whole GOP. Or I was just wondering what the distribution of scores looked like if you started to dig into the GOP.
That's a good question. Yeah. So a lot of the things I'm reporting are averages over all the frames. And what is the distribution? Yeah, because of the nature of the shots, I have to say, except for the wave sequence, I mean, the picture behavior is pretty homogeneous. You would think that scene where the train comes into view wouldn't be, but actually it was quite well behaved. So most of the distribution is relatively tight, but that waves one is a challenge, definitely. But I think is a challenge full stop if you look at that picture content. Yeah.
Further questions?
Oh, there's one.
Thank you very much. Very naive question. If we're using LED wall technology to do virtual production, we're already rendering on the spot. What is the benefit of compressing between the renderer and the screen itself?
So good question, but actually there's two different modes of operation of virtual production walls, right? And for instance, this morning, Lawrence Sher was saying that, they shot background plates and drove the screen with those pre-baked background plates, right? And so there are actually two modes in which you would drive the wall. One is using Unreal Engine and drive the wall, and then the other one is actually go out and shoot the background plates. And there are good reasons in both cases. As when you have more complicated scenes to render, actually just shooting the shot beforehand is a practical solution, which is what they did in particular shoots.
Thank you. A follow-up question, which I don't mean to be a bummer, but we're not looking at a significant volume of content on a film production. Do we really have significant savings by compressing those versus running from an uncompressed server?
Yeah, you'd think that. But actually, for some of these loops, you need, kind of enough content for the scene to be natural during the shoot, right? So, many minutes of content, right? And actually pushing them around the production house and then pushing them into the cloud over in Los Angeles and downloading it in our house in London for the shoot is a pain. And especially when you might want to do things to the background plates in some intermediate step, right? In fact, just doing this experiment, we really began to appreciate how tricky it is to shove that amount of data up to the cloud. And it wouldn't seem like a lot, but if you could reduce that size by a factor of 20, you take it. All right.
Further questions? Maybe I try a question. Have you thought about other codecs like JPEG XS, what we heard today in the morning, or NDI, which are also quite common in as contribution codecs?
Yeah. So we didn't do the comparison with JPEG access at the time, we were limiting ourselves to what was available cheaply on the NVIDIA chipset, but definitely something to throw into the mix here and see how it works. The one thing I noticed, though, from the talk this morning was that the bit rates that were being discussed still in excess of 1 gigabit per second. And I think for this particular application, you could get away with a lot less.
No, thank you. It was a great presentation, but I want to follow up on that JPEG XS because a UHD feed, 12 gig, you break it up into 4 quadrants and you can do it at 270 meg each and mux it back together. I'm in the transport business and I have to get signals compressed between 2 separate facilities. And the efficiency of the bandwidth utilization, especially if customers have multiple signals that they want to get, let's say from a racetrack or a baseball game, multiple cameras. I'm very intrigued with how, that would work, and especially with 2110, the HEVC is, one thing, but to then take it a step further, that's where the efficiency really comes in. Don't you think? Or
yeah, no, you're right.
Please.
In fact, try and see, deploy these things inside as packets inside 2110. Then we got wrapped up in just verifying that the quality was okay. So that's definitely something to look at. And in general, this is just my personal opinion that in post-production or in these sort of high-quality environments, there's a lot of scope for hybrid video codecs, which hasn't really been explored yet, just because they tend to be tricky to use. But in these simple invocations, like this is just default invocation, it's pretty straightforward to use. Just a matter of getting the word out there and maybe providing some of the infrastructure to make it easier. That's all. But yeah, you're right. Using this as a transport in those sort of high quality environments could help a lot.
Yeah, thank you. Fritz Fösel from Fraunhofer IIS. We co-developed JPEG XS, and I will not ask about JPEG XS. My question is more about how much latency do you expect is okay for virtual production?
It's another good question. And the guys in disguise always tell me, when I ask them that question, how much more latency you could tolerate, they say no more. No more than what we have now. But yeah, it seems that one frame latency is the most anybody could tolerate, and which is why I limit things here to intra-coded frames and P frames only. So then your problem becomes memory in your decoder, but that seems to be more or less solved right now. But you're right, that is a big constraint.
Okay, last question. Coming.
I'm just going to question that last point because it's pre-recorded. Started 100 milliseconds earlier.
So that's what I used to think until in virtual production you realize when the camera moves, you want to slightly change the view, right? So even with pre-baked plates, there is a pre-process where you do some sort of 2.5D depth extraction so that when you move the camera a little bit, you could get a little, twist in the render. And that means that you have to keep up, right? So when I do this, I have to re-render and so on. So yeah, I think you're right though that, we should be able to build in a one frame, buffer there somehow, but it's just two different technologies to interoperate, and people haven't gotten to that point yet, but totally doable. Yeah.
Okay, thank you. I think this is a topic which has more room for discussion. Thank you, Anil.